Angle between two lines using direction ratios. Welcome, everyone. Today we are going to explore a very important concept in three-dimensional geometry, finding the angle between two lines using direction ratios. To start off, let's set the stage. In a three-dimensional space, a line isn't just defined by a single point, but by its orientation, that is, the specific direction in which it points. We use a set of values called direction ratios to mathematically define this orientation. Now, if we have two different lines and we want to determine the angle between them, we aren't just looking at the lines themselves, but rather at the directions they are traveling. Essentially, finding the angle between two lines is the same as finding the angle between the specific directions in which these lines extend. Over the next few slides, we will look at how to use these ratios to calculate that exact angle using a precise mathematical formula. Understanding the concept. Now that we've established that the orientation of a line in 3D space is defined by its direction ratios, let's dive deeper into what these numbers actually represent. Think of direction ratios as a set of three numbers. Let's call them A, B, and C, which are proportional to the direction cosines of the line. While direction cosines are specific values, direction ratios are essentially a scaled version of them, making them much easier to work with in calculations. To apply this to our goal of finding an angle, let's imagine we have two lines, L sub 1 and L sub 2, both passing through the origin. To find the angle between them, we first need to represent their directions using their respective direction ratios. For our first line, L sub 1, we'll use the set A sub 1, B sub 1, C sub 1. For our second line, L sub 2, we'll use A sub 2, B sub 2, C sub 2. The angle theta that we are looking for is simply the angle between the vectors that these ratios represent. One important thing to keep in mind before we move on to the actual formula in the next slide. By mathematical convention, when we talk about the angle between two lines, we are almost always referring to the acute angle. This means we are looking for the smaller angle, the one that sits between 0 degrees and 90 degrees. Keep this in mind, because as you'll see in a moment, our formula includes a special feature to ensure we always get this acute result. The mathematical formula. Now that we understand that direction ratios represent the orientation of our lines, let's look at the actual mathematical formula we use to calculate the angle between them. To find the acute angle theta between our two lines, L1 and L2, we use this formula. Cosine theta equals the absolute value of A1 times A2 plus B1 times B2 plus C1 times C2, all divided by the quantity, the square root of A1 squared plus B1 squared plus C1 squared, multiplied by the square root of A2 squared plus B2 squared plus C2 squared. Now, I want you to pay close attention to those vertical bars surrounding the fraction. These bars denote the absolute value. This is a crucial detail because, by taking the absolute value, we ensure that the value of cosine theta is always non-negative. In trigonometry, a non-negative cosine value guarantees that the angle theta we calculate will be an acute angle, meaning it stays between 0 and 90 degrees. We will see exactly how this works in practice when we walk through the step-by-step calculation in the next slide. Step-by-step calculation process. Now that we have seen the formula itself on the previous slide, you might be wondering how to actually approach a problem without getting lost in all those variables. So, let's break this down into a clear step-by-step calculation process that you can follow every single time. First, your starting point is to identify the direction ratios. You'll need to look at your given lines and extract the three numbers for the first line. Let's call them A sub 1, B sub 1, and C sub 1, and do the same for the second line, which we'll call A sub 2, B sub 2, and C sub 2. Second, we move to the numerator. This is where you find the sum of the products of the corresponding ratios. Specifically, you'll multiply A sub 1 by A sub 2, B sub 1 by B sub 2, and C sub 1 by C sub 2, and then add those three results together. Third, we need to tackle the denominator. This part has too many steps. First, calculate the magnitude of the first direction by taking the square root of A sub 1 squared plus B sub 1 squared plus C sub 1 squared. Then, do the exact same thing for the second direction. The square root of a sub 2 squared plus b sub 2 squared plus c sub 2 squared. Once you have both these square roots, simply multiply them together. Fourth, it's time to apply the formula. Take the sum you calculated in step 2 and divide it by the product you found in step 3. And, as a very important reminder from our previous slide, don't forget to take the absolute value of this result to ensure we are working toward an acute angle. Finally, once you have that single numerical value, you'll find the actual angle, theta, by using the inverse cosine function, or arcos. If you follow these steps carefully, as I'm about to demonstrate in our next slide with a real-world laser beam example, you'll find that even complex-looking 3D problems become quite manageable. Real-world example. Now that we have covered the theory and the formula, let's put everything we've learned into practice with a real-world example. Imagine you are in a laboratory, and you have two laser beams originating from a single point, which we can call the origin. The first beam, let's call it L1, follows the direction ratios 1, 1, 0. The second beam, L2, follows the direction ratios 0, 1, 1. Our goal is to calculate the exact angle, theta, at which these two beams diverge from each other. Let's walk through the solution step by step, following the process I outlined in the previous slide. Step 1. First, we clearly identify our direction ratios. For our first line, L1, we have a sub 1 equals 1, b sub 1 equals 1, and c sub 1 equals 0. For our second line, L2, we have a sub 2 equals 0, b sub 2 equals 1, and c sub 2 equals 1. Step 2. Next, we calculate the numerator. We need to find the sum of the products of the corresponding ratios. So, we multiply 1 by 0, 1 by 1, and 0 by 1. This gives us 0 plus 1 plus 0, which results in a numerator of 1. Step 3. Now, let's calculate the denominator. We need the magnitude of each direction. For the magnitude of L1, we take the square root of 1 squared plus 1 squared plus 0 squared, which simplifies to the square root of 2. For the magnitude of L2, we take the square root of 0 squared plus 1 squared plus 1 squared, which also simplifies to the square root of 2. To get our denominator, we multiply the square root of 2 by the square root of 2, which gives us exactly 2. Step 4. Now, we apply the formula we discussed earlier. We take the absolute value of our numerator divided by our denominator. This gives us the absolute value of 1/2, which is simply 0.5. Step 5. Finally, we find the angle. We take the inverse cosine of 0.5, which results in an angle of 60 degrees. So, to conclude our calculation, we can see that the two laser beams diverge at an angle of 60 degrees. As you can see, when you follow the steps methodically, even three-dimensional geometry becomes quite manageable. But before we wrap up, I want to point out a few common pitfalls to watch out for in your own calculations. Common mistakes to avoid. Now, before we wrap up our lesson and move on to the final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula, small errors can lead to the wrong answer. First, please be very careful not to ignore the absolute value. As we used in the formula on slide 3, those vertical bars are crucial. If you forget them, you might end up with a negative value for cosine theta, which would actually give you the obtuse angle, the larger angle, instead of the acute angle we are looking for. Second, watch out for incorrect pairing. When calculating the numerator, you must multiply the corresponding components. A 1 times a 2, b1 times b2, and c1 times c2. If you mix these up, your entire numerator will be incorrect. Third, keep a close eye on your calculations involving square roots. A very common mistake is a sign error when squaring negative direction ratios. Always remember that -2 squared is +4, not -4. Finally, don't confuse direction ratios with direction cosines. While they are related, direction ratios can be any set of numbers, whereas direction cosines must satisfy the condition that L squared plus M squared plus N squared equals 1. The formula we have been practicing today is specifically designed for using direction ratios. Keep these points in mind, and you'll be well on your way to mastering this topic. Key takeaways. First, remember that the fundamental principle we've explored is that the angle between two lines in three-dimensional space is determined entirely by the relationship between their direction ratios. Essentially, if you know how the lines are oriented, you know the angle between them. Second, I want you to keep that main formula in your mind. It is cosine theta equals the absolute value of a 1, a 2 plus b1, b2 plus c1, c2 all over the square root of a 1 squared plus b1 squared plus c1 squared multiplied by the square root of a 2 squared plus b2 squared plus c2 squared. Now, it might look a bit intimidating, but remember that this formula is actually derived from the dot product of two vectors, which is a concept you'll see frequently in vector algebra. Third, a very important point to remember, and something we highlighted in our common mistakes slide, is the use of the absolute value bars. We use the absolute value to ensure that the resulting cosine value is non-negative, which guarantees that the angle theta we calculate is the acute angle, rather than the obtuse one. Finally, let's look at the structure of that formula one more time. The denominator is not just a random set of numbers. It represents the product of the magnitudes of the direction vectors of the two lines. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. If you can master these points and practice the step-by-step process we went through in our example, you'll be well prepared for any problem involving the angle between lines. Great job today.